Hello, welcome to AP Statistics, Chapter 18, video number 1. There will be 2 videos. Today we're going to talk about sampling distribution models. Okay, so we're going to learn about 2. The sampling distribution model for sample proportions and for sample means. So the central limit theorem for sample proportions. Suppose we were to draw many samples and looked at the distribution of sample proportions for these samples. Just like we looked at the distribution of the samples where we looked at the proportion of 20 pennies that were 2002 or later. Okay. The histogram we get, if we could see all the proportions from all possible samples, is called the sampling distribution of the proportions. So for the pennies, we looked at some of the samples. Of course, we didn't look at all of them. That would have taken a lot longer than we had to look at them. And so we created part of the sampling distribution, but if we'd been able to look at them longer and create all of them, we would have had the whole sampling distribution. So what would the histogram of all the sample proportions look like? Well, the histogram of the sample proportions would center at the true proportion P in the population. As far as the shape of the histogram goes, it would be unimodal and symmetric. More specifically, it's an amazing and fortunate fact that a normal model is just right for the histogram of sample proportions, and that works out really well for us. Modeling how sample proportions vary from sample to sample is one of the most powerful ideas we'll see in this course, and that's why we took the time to look at the penny problem. A sampling distribution model for how a sample proportion varies from sample to sample allows us to quantify the variation and the likelihood that we'd observe a sample proportion in any particular interval. And so the likelihood there, that's another way of saying probabilities. It's normal, so we'll be doing z-scores and normal CDF. To use a normal model, we need to specify its mean and standard deviation. We'll put mu, the mean of the normal, at P, the population proportion, what we're trying to estimate with the P hats. When working with proportions, knowing the mean automatically gives us the standard deviation as well. The standard deviation we will use is square root of P times Q over N, and remember Q is just 1 minus P. So the distribution of the sample proportions is modeled with a probability model that is normal with a mean of P and a standard deviation of the square root of P times Q over N. So you need to know that. So that's one of the things you need to memorize, is the distribution of the sample proportions is modeled by normal, mean of P, standard deviation of square root of PQ over N. So here's a picture of what we just discussed. So here we've got the mean at P, where we've got 1 standard deviation to the left, 1 standard deviation to the right. So that's why they've got -1 square root of PQ over N, 1 square root of PQ over N, and then we've got 2 out and 3 out. So we'd expect 68% of sample proportions to be between -1 standard deviations and +1 standard deviations. We'd expect 95% to be between -2 standard deviations, +2 standard deviations, and 99.7% to be between -3 and +3 standard deviations, because this is a normal model and the 68, 95, 99.7 rule applies. So because we have a normal model, for example, we know that 95% of normally distributed values are within 2 standard deviations of the mean. That's just what I was talking about. So we should not be surprised if 95% of various polls give results that were near the mean but varied above and below that by no more than 2 standard deviations. So we expect there to be some sampling variability. That is what we mean by sampling error. It's not really error at all, but just variability you'd expect to see from one sample to another. So really a better term is sampling variability, but they mean the same thing. So how good is the normal model? The normal model gets better as a good model for the distribution of sample proportions as the sample size gets bigger. Just how big of a sample do we need? This is going to be revealed in just a minute. There are some assumptions we have to make and conditions we have to check in order to make those assumptions. Most models, in fact, are useful only when specific assumptions are true. There are two assumptions in the case of the model for the distribution of sample proportions. College Board places a high priority on you being able to know what assumptions you're making and knowing what conditions to check to be able to make those assumptions safely. So this is extremely important for you to know for both the sampling distribution for proportions that we're talking about right now and the one for means that we'll talk about in just a minute. Okay, the first one is the independence assumption. The sampled values must be independent of each other. Okay, that's why when we would sample 20 pennies, we put them back in and mix them up before we sampled 20 more. The sample size assumption, the sample size n must be large enough. Assumptions are hard, often impossible to check. That's why we assumed them. Still, we need to check whether the assumptions are reasonable by checking conditions that provide information about the assumptions. Okay, so we can check conditions, and the whole reason we check them is so that we can make the assumptions we need to make. The corresponding conditions to check before using the normal distribution to model the distribution of sample proportions are the randomization condition, the 10% condition, and the success-failure condition. For the randomization condition, the sample should be a simple random sample of the population, okay? Or at least it should be a sample where we can assume it acts like a simple random sample of the population. Number two, the 10% condition, the sample size n must be no larger than 10% of the population. It's just that if our sample size is too large relative to the population size, the methods we do won't work. There's ways to adjust for it. That's beyond the scope of the course. So for us to use our methods, we need the sample size to be no larger than 10% of the population. And an easier way to check that, perhaps, is to make sure that the population is at least 10 times as large as the sample. So the size of the population needs to be larger than 10 times n. The success-failure condition, this is how we know the sample size is large enough. The sample size has to be big enough so that both n times p, the number of successes, and n times q, the number of failures, are at least 10. So we need a large enough sample that's not too large. So 2 and 3 together kind of work to be the Goldilocks kind of conditions together, that the sample size is just right. A proportion is no longer just a computation from a set of data. Of course, that's what, on one level, what it is. But it's also now, we can think of it as a random variable quantity that has a probability distribution. That's what the sampling distribution is. So when we did the penny activity and we looked at the proportion of those 20 pennies that were 2002 or later, we were getting a computation from that set of data, but it was a random variable quantity because the next time we put those pennies back in, mix them up, drew another 20 out, we had no way of knowing exactly what that proportion was going to be ahead of time. It's numerical, it's a result of random activity, so it fits that definition of random variable quantity. Even though we depend on sampling distribution models, we rarely get to see them. Like I said, even when we did the penny activity, we only saw a partial sampling distribution model. So to be able to create the whole thing, that would take a tremendous amount of time. We rarely take those repeated samples from the same population and make a histogram. We only imagine or simulate them. Still, sampling distribution models are important because they act as a bridge from the real world of data, what you actually get from the single sample that typically you take. Typically, you just take one sample and get the proportion from that, to the imaginary world of the statistical model, and they enable us to say something about the population when all we have is data from the sample. So what it does is it lets us draw inferences to say, here's what happened in my sample based on what we know about sampling distributions. This is what it says about the population. Provided that the sampled values are independent and the sample size is large enough, the sampling distribution of p hats, those sample proportions, is modeled by a normal model with a mean, mu of p hat equaling p, the population proportion, and standard deviation of p hat equaling the square root of p times q over n. So what about quantitative data? Proportions summarize categorical variables. So we're working with categorical data when we're working with proportions. What about quantitative data? The normal sampling distribution model looks like it could be useful. Can we do something similar with quantitative data? We can indeed. That's why we spend so much time talking about normal models, because they're just so useful for us. Even more remarkable, not only can we use all of the same concepts, but almost the same model. Like any statistic computed from a random sample, a sample mean also has a sampling distribution because it is a random variable. We can use simulation to get a sense as to what the sampling distribution of the sample mean might look like, and that's what we're going to do in a second. We also did that when we did the penny activity. Remember, we looked at the average age of individual pennies, and that would be with the sample size of 1, or just at the actual distribution of the actual population. But then we looked when we had 5 pennies, and we looked at the average. Okay, we were developing at least part of the sampling distribution where n is 5 and looking at the average, and then we looked at it when n is 20. And so remember, for n equals 20, we got the sample mean as well as the sample proportion. So what we're going to do now is we're going to look at another case and use simulation to see what we get. All right, so this is the average of one die. Let's start with a simulation of 10,000 tosses of a die. So this is where n equals 1. We're just looking at the tosses of a single die, but we're going to repeat that 10,000 times. A histogram of the results is kind of what we would expect it to be, pretty uniform there. Looking at the average of 2 dice, so we're going to take 2 dice, see what they get, average them together, so n is 2. After a simulation of 10,000 tosses, look how much more normal this looks. It's single peaked, it's symmetric, it looks much more normal. Let's increase n even more. The average of 3 dice after a simulation of 10,000 tosses looks even more normally distributed there, and the reason it's more normal looking is because the tails are smaller, in case you're going, but I thought where n equals 2 it was really normal looking. Yeah, but it's got a lot more observations in the tails. As n gets larger, where we have n equals 5, n equals 20, we get a much more normal distribution. But if you look, the center is always around that 3.5. Okay, always around that. Okay, because 1 plus 6 divided by 2 is 7, and everything's kind of, 1 plus 6 is 7, divided by 2 is 3.5, and everything is centered around that. Okay, so what does this simulation show? As the sample size, the number of dice, gets larger, each sample average is more likely to be closer to the population mean. So we can see the shape continuing to tighten around 3.5. And it probably does not shock you that the sampling distribution of the mean becomes normal. The sampling distribution of any mean becomes more nearly normal as the sample size grows. All we need is for the observations to be independent and collected with randomization. We don't even care about the shape of the population distribution. Back to the pennies, it was skewed when we looked at just the population distribution, but when we looked at the average when n was 5, it became more normal, and then with n equals 20, much more normal. The fundamental theorem of statistics is called the central limit theorem, which can be abbreviated CLT. Everybody knows that means central limit theorem. The CLT is surprising and a bit weird. Not only does the histogram of the sample means get closer and closer to the normal model as the sample size grows, but this is true regardless of the shape of the population distribution. And that's so cool. So like the pennies where the population distribution was skewed, still once we start averaging, the sampling distribution of the sample means gets closer and closer to the normal model. The CLT works better and faster the closer the population model is to a normal itself, it also works better for larger samples. So if your original population is symmetric, your sample size for your mean can be smaller in order to get closer to the normal distribution for the sampling distribution of the mean. But even if it's skewed, the original population, CLT works for larger samples. So, central limit theorem. The mean of a random sample is a random variable whose sampling distribution can be approximated by a normal model. The larger the sample, the better the approximation will be. The CLT requires essentially the same assumptions we saw for modeling proportions. There's an independence assumption and there's a sample size assumption. The independence assumption states that the sampled values must be independent of each other, and the sample size assumption says that the sample size must be sufficiently large. Okay, so we can't check assumptions, so we have to think about whether the independence assumption is plausible, and we can also check some related conditions. So you stop and think, okay, is it reasonable that the age of one penny that I draw from this population is going to be independent of the age of another penny drawn from the population? Randomization condition needs to be checked. The data values must be sampled randomly. Okay, and 10% condition. When the sample is drawn without replacement, the sample size n should be no more than 10% of the population. So, for instance, with the pennies, I needed to make sure that our sample size was less than 10% of my whole population of pennies, because when you did draw them, it's not like you noted what one year on the penny was and then put it back in the box and mix it up. You drew out all 20 without replacement. Large enough sample condition. The CLT doesn't tell us how large a sample we need. For now, you need to think about your sample size in the context of what you know about the population and that the sample is large enough. Later on, when we actually start using the sampling distribution for means to do our inference, we'll talk about how large this needs to be. So with the difference here is that we don't have a success-failure condition, we just have large enough sample condition, and that's because you don't have the concept of success and failure for quantitative data. You just have measures. For proportions, you have success in either demonstrating the characteristic of interest, or it fails to demonstrate the characteristic of interest. So that's why for proportions we had the success-failure condition. Okay. But which normal? The CLT says that the sampling distribution of any mean or proportion is approximately normal. But which normal model? For proportions, the sampling distribution is centered at the population proportion. For means, it's centered at the population mean. So for sample means, for y bars, it's centered at the population mean, mu. But what about standard deviations? The normal model for the sampling distribution of the mean has a standard deviation equal to, standard deviation of y bar equals to sigma over the square root of n. So the standard deviation of the population of all the y's, of all the observations, divided by the square root of n, that's the square root of the sample size. So sigma is the population standard deviation. The normal model for the sampling distribution of the proportion has a standard deviation equal to the square root of PQ over N. So that can also be written as this square root of PQ over the square root of N. So it's very similar to our standard deviation for means. It's just instead of square root of PQ, you have little sigma. Both of them divided by square root of N. The standard deviation of the sampling distribution declines only with the square root of the sample size, because the denominator contains the square root of n. Therefore, the variability decreases as the sample size increases, and that is something you need to know. The real world and the model world. Be careful. Now we have two distributions to deal with, and they sound very similar. The first is the real-world distribution of the sample, the actual data that we're examining, which we might display with a histogram. The second is the math world sampling distribution of the statistic. So of the p hat or of the y bar, which we model with the normal model based on the central limit theorem. Don't confuse the two. Okay, and if you look, the grammar here is extremely important. The distribution of the sample is something completely different from sampling distribution. And so that's just something you need to know and be very careful about how you read and also how you write. Always remember that the statistics itself is a random quantity. It acts as a random variable. We don't know what our statistic will be because it comes from a random sample. Okay, we don't know what p hat's going to be or what y bar is going to be before we take our sample. Okay, we take a random sample and we discover what it is. Fortunately for the mean and proportion, the CLT tells us that we can model their sampling distribution directly with the normal model, which is great because, you know, we can figure normal probabilities. It's available, boom, easy on our calculator. There are two basic truths about sampling distributions. Sampling distributions arise because samples vary. That's why we don't just have a single value, why we have a whole distribution of value. Each random sample will have different cases, and so a different value for that summary statistic, whether it's a proportion or whether it's a mean. Although we can always simulate a sampling distribution, the central limit theorem saves us the trouble for means and proportions. We love the central limit theorem. Okay, I'm going to stop here. For video 1, we're going to come back on video 2, talk about what can go wrong, and then look at some examples. All right, I'll see you again in just a minute.